Hey guys, here I am, it's calculus time. Tonight I'm talking about the second derivative test. Now this really is kind of pedantic. It's not really necessary. However, AP might ask a question regarding this. Hopefully this will make sense to what we're doing in light of what we've been doing. Right now I've got the function f of x equals x quantity x minus 4 cubed. Now, as you recall, I did this problem before when I was finding the points of inflection and the concavity. Here's the graph of that. All right. Now, we've also learned how to find critical values. We know that critical values are either relative maxes, relative mins, or points of inflection. Right. Now, if I take a look at this, all right. I've taken the first derivative of this function, and I've taken the second derivative of this function, right? Everybody see the first derivative and the second derivative, right? Take a look at how I can apply both of those derivatives to the second derivative test, all right? Well, here's what the first derivative says. The first derivative says, if I set the derivative, the first derivative equal to 0 and solve, I get my critical values, which would either be turning points or which would either be local maxes, local mins, or points of inflection. So if I solve these, I get the first parenthesis x equals 4, and from the second parenthesis x equals 1, right? So I know that at x equals 1, I've got some kind of turning point, or some type of critical number. Now, if you look at the graph, I know it's a local minimum, right? I know that at x equals 4, I've got some kind of critical number. And again, that's going to be either a local min, local max, or some type of point of inflection. Well, here is what we can say. When I set my second derivative equal to 0 to find my points of inflection, like I just did in the previous screencast, I got x equals 4 and x equals 2. Agreed? Right? Well, so I know that on my number line for my points of inflection for my second derivative, if I make this f double prime, I've got 2 and I've got 4. I know that the derivative, the second derivative equals 0 here, right? So f double prime equals 0 here, and f double prime equals 0 here, right? Well, we know that we could test concavity in each of these three intervals. To the left of 2, between 2 and 4, and to the right of 4, right? Well, would you agree that my critical numbers, such as x equals 1, I know that 1, that had to be in this interval to the left of 2. Well, let's see here. And by the way, we know that from the picture, we know that that 1 is the local minimum. We know that, right? Well, let's see if this makes sense. If I were to plug in f double prime at 1 and evaluate, what kind of answer would I get? Well, does it make sense that since it's in a concave up region, I know that I better get a positive value? And again, if I tested 1, f double prime at 1, let's see what I get. F double prime at 1 gives me 1 minus 4 times 12 minus 24, which is equal to negative 3 times negative 12, so positive 36. And again, since that's positive, I know it's concave up, right? Well, does it make sense that if we put the two ideas together, I knew x equals 1 was a critical number. So again, it either produces a local min, a local max, or a point of inflection. But since I know that 1, when I plug in 1 to the second derivative, it must be in a region that's concave up. Well, gosh, the only type of important points that are concave up are local minimums, right? Does that make sense? Similarly, if I did this with my other critical number of 4, right? Suppose I did this with 4. When I plugged in 4 here, do I get a positive number for f double prime, a negative number for f double prime, or 0? Well, gosh, I got 0, right? So if if f double prime of 4 is equal to 0, gosh, that means it's not in any type of concavity. It must be a point of inflection. So ultimately, here's what I'm trying to get at. Here are my rules for the second derivative test. All right? All right? For my second derivative test, right? If I first find my critical values from f prime of x, right? Now, how do I do that? Again, you set f prime of x equal to 0, right? All right? Now, secondly, if I find the second derivative of x, right? Well, now, if I test the critical values from the first derivative, if I test these numbers that I created in the derivative in f double prime of x, and I get these following results, here's what I know. Right? If f double prime of x is positive at the critical value, I can assume that critical value produces a relative minimum value. Okay? If f double prime of x is greater than 0, is less than 0 at the critical value, then that critical value produces a relative maximum turning point. And then for the last scenario, if f double prime of x is equal to, if f double prime of x is equal to 0 at the critical value from f prime of x, then that critical value is a point of inflection. Okay? Now again, we rarely use that. Now, let's take a look at an example where we use the second derivative test. It says use the second derivative test to find all relative maximum and minimum points for the function f of x equals sine of x plus cosine of x on the interval of 0 to 2 pi. All right? Actually, this is a takeoff of a problem that I think Rafa was asking about in class. So here we go. So according to my second derivative test, here's what I want to do. I want to find my my first derivative. Actually, let me change that. Before we do that, let's take a look at what this function looks like. Right? This function looks a little like this. Right? I've typed this in, sine of x plus cosine of x. This is the graph of it. What am I looking for? And by the way, the domain of that, this goes from 0 on the x-axis to 2 pi. That actually ends at 2 pi. So where are my relative mins and maxes? They're right here and right here. So I know I'm going to come up with one relative max and I'm going to come up with one relative min. Okay? These are, by the way, in increments of pi over 2s. Right? So it looks like that might be at pi over 4, right? So hopefully we can get a relative maximum in pi over 4s. And let's see if that's pi. Let's see here. That would be right here, pi. This looks like it might be at maybe 3 pi over 2. Let's hope. Let's hope for the. I'm sorry, 3 pi. No, I'm lying with eyes. That might be at what would that be? 5 pi over 4. That's what I'm thinking. Let's hope. Right? Okay. But let's test. So let's see here. If I were to by graph, all right. If I were to use my second derivative test, it says find the first derivative. Well, the first derivative will be the derivative of sine of x is cosine of x. and the derivative of cosine of x is negative sine of x, okay? If I set this equal to 0, I get 0 equals cosine of x minus sine of x, okay? Solving, gosh, I'm not a big fan of what I see here. So what am I going to do here? I'm going to separate these. Isn't it true that sine of x equals cosine of x? Now, I can kind of, again, reason this out. I know that the only time that would occur would be in the first quadrant and in the, third quadrant, and that would occur at pi over 4 and at 3 pi over 4, right? But let's see, algebraically, how can I solve this? Well, let's see here. I know that sine x doesn't have a trig identity unless it's squared. So here I'm going to square both sides. I'm going to square this side and get sine squared of x equals this side squared is cosine squared of x. Agreed? Now, because of this, and it doesn't matter which one you do, I'm going to get rid of this sine square, this cosine squared on this side. Isn't it true that this is equal to what is that? 1 minus sine squared of x? Agreed? Well, now if I make everything come to this side, wouldn't I get what is that? 2 sine squared of x minus 1 equals 0? Well, now that I have just the word sine in there, I can just solve this by SAD mapping. I could, well, you guys are better than this. I could just get sine squared of x equals a half, square root, and I get sine of x equals positive negative root 2 over 2. So sine of x equals root 2 over 2, or sine of x equals negative root 2 over 2, right? And in what quadrants would that occur? Well, sine of x, where does that occur? At x equals pi over 4 in the first quadrant, and at, what is that, at 3 pi over 4 in the second quadrant. And where does it equal negative root 2 over 2? Well, it's negative in the fourth quadrant, so 5 pi over 4, and at 7 pi over 4, right? So according to this, geez, Pete, I came up with 4 critical values. Pi over 4, 3 pi over 4, 5 pi over 4, 5 pi over 4, and 7 pi over 4. Does that jive with what we said my graph is going to look like? I thought I had 1 relative max and 1 relative min on this interval. Hey guys, let's hold on tight. Let's see where this takes us. All right, so let's go on. So now, according to my second derivative test, I found the critical values for my first derivative, and now I'm going to find the actual second derivative of my function. Well, again, coming back all the way up to here, this was my first derivative, right? So let's take him, throw him down. Let's take a look. So this is my first derivative. Let's take the second derivative now. So that second derivative in terms of x would be, let's see, the derivative of cosine of x is negative sine of x. And the derivative of sine of x is cosine of x, so minus cosine of x, right? Okay? So this is my second derivative. Well, here's what the second derivative test says. If I take these 4 values that I got, pi over 4, and what was the other one? Let's see here, 3 pi over 4, at 5 pi over 4, and at 7 pi over 4, if I plug these values in for x here and here, let's see what happens. So let's see, f prime at pi over 4. What do I get? Well, let's see, I get negative sine of pi over 4 minus the cosine of pi over 4 yields, well, the sine of pi over 4 is negative root 2 over 2 minus root 2 over 2 again, right? That's cosine of pi over 4, which is negative root 2, right? Well, because that's negative, if the second derivative produces a negative, I know that this graph must be concave down. And so that critical value of pi over 4 must produce a relative max. So I know at pi over 4, there is a relative max. Okay? Let's test the next one. So he's done. Now let's do 3 pi over 4. So if I test 3 pi over 4, I get, let's see here, that would be negative sine of 3 pi over 4 minus cosine of 3 pi over 4. Let's see what that equals. The sine of 3 pi over 4, that's the second quadrant. Sine's positive in the second quadrant, so root 2 over 2. So positive root 2 over 2, but that negative is there, right? So negative root 2 over 2 minus the cosine of 3 pi over 4. Well, again, cosine of pi over 4 is root 2 over 2. But in the second quadrant, cosine produces negative fraction. So, oh, wait a minute. That becomes minus the negative becomes positive root 2 over 2. Oh, wait a minute. Isn't that 0? Wait a minute. Golly, I think I remember saying something about that. Well, wait a minute. Oh, wait a minute. Is the second derivative is equal to 0, I know that critical value must have been also a point of inflection. In other words, my concavity must have changed. Oh, yeah. So, right here at that, this was where we have, what is that, that value, 3 pi over 4? That's where my concavity changed, and I didn't even think about that. Golly. All right, now let's go on. So, testing, the next one I got was 5 pi over 4. I think you should know we should get a positive number here, but let's just check it. Negative sine of 5 pi over 4 minus cosine of 5 pi over 4 gives me, let's see, the sine of 5 pi over 4 is radical 2 over 2, but it's in the third quadrant, so negative, so that becomes a positive, minus the cosine of 5 pi over 4 is, well, cosine of pi over 4 is, again, root 2 over 2. But in the third quadrant, that's negative. Oh, that becomes positive. So don't you get, oh, wait, this is positive root 2? And again, because it's positive, again, we know with concavity, if it's concave, if it's positive for the second derivative, I know that's concave up, correct? Because my slopes are increasing. Oh, wait a minute. So that must mean that must be a relative minimum. So I know that at 5 pi over 4, you get a relative minimum, right? Okay? So, can you see that I've used the first derivative and the second derivative to figure out whether a critical value is a relative max or a relative min instead of using the sign charts that we did with the first derivative? And this is just an alternative to, again, using the first derivative in a sign chart. Okay? Well, I think I've talked enough, so I'll talk to you later.